And welcome to the next U of T AI and Robotics seminar. So today we have Guanya, who is a PhD student at Caltech, and he's going to be presenting about the neural lander family. So thank you for presenting, and yeah, let's get on one.
Okay, thanks, Arthur, for the introduction. I really like the seminar you're hosting. I think it's really good to have such things in a pandemic. Right. So today I'm very happy to be here with and to present our recent work on neural lander family, learning-based nonlinear stable control in challenging environment. I call this family because it's really a lab work. It's basically three papers. We all show like kind of new capabilities in these three papers. The first one is called neural lander, which we essentially show like smooth and fast landing compared to the baseline. The second one is called neural swarm. As you can see from this video, we achieve a close proximity swarm flight. And then third one is called a neural fly. As you can see from here, we achieved like very good flight performance in time variant in time variant environment. For example, if I turn on the wind, I can still control the drone very well. Okay, let's start. By the way, if you have any question, feel free to interrupt me during the process. So the motivation is actually the real world decision making is very hard. So here comes an interesting question. Can we broaden the successful horizon of deep learning? So why I said broaden, because deep learning proves very successful in a lot of applications in this box in decision making. For example, it can play the Atari game much better than human. For example, in Go, it defeat the world championship. And for example, the OpenAI manipulator can solve very complex Rubik cube problem. However, it remains unclear whether we can extend this success to some other real-world problems in this box. For example, here's a quote from Aerospace Corporation director when he visited Caltech. I want to use deep learning to optimize the design, manufacturing, and operation of our aircrafts, but I need some guarantees. Yeah, apparently he has a reason to ask this question because if you notice in the applications in the left-hand side, we actually don't care about too much about failure and safety. For example, we don't care if the Rubik cube is dropped, if it drops or if it breaks the Rubik cubes. And apparently we care this a lot in some other applications like aircraft. And also another reason why he asked this question, because the aerospace already achieved extraordinary safety level. Here is a screenshot of Professor Richard Murray's talk at some workshop. Can we really use machine learning in safety critical system? He reported some interesting numbers here. So the question is, how safe do autonomous vehicle need to be compared to some existing transportation? For example, the human-driven cars, there are 7 deaths every billion miles in the United States, and the number decreased to 0.1 to 0.4 if you choose buses and trains, as the number further decreased to 0.07 every billion miles if you use airplanes. So that means we need to convince the government, the investor, the customer enough. Like if we combine deep learning in these protocols, can we show such level of safety? So can we like guarantee something? It's basically the motivation of my work. Okay, so let's kind of summarize where the challenges from where the challenges from in the right hand side compared to the left hand side. So the first thing is uncertainty. We all have a kind of modeling mismatch, sim to real gap. For example, here's the Caltech cast fan wall. When you turn on the wind, you have a totally different dynamics compared to no wind case. And the second is pretty much, especially in robotics, we all know like a robotics experiment is hard because we have a lot of things different from simulator, including a delay, motor failures, like saturation, blah, blah, blah. And a second big reason is limited computational power, right? For example, here is some drone I use in my experiment called Crazy Fly. It's only 34 grams, it's super light. Apparently you cannot have GPUs on that, right? To run complex neural networks. So we have to think about how to make things compact and efficient. And also data collection is not cheap. And third reason is basically we need some formal interpretability. One example is causality. Another example is in control sense, like stability and safety. Stability essentially means, as you can see from this figure, if you perturb the trajectory a little bit, it can stay in a bounded tube. At least tells you it can be like safe around the equilibrium point. However, the neural networks in general hard to control. Here is a landscape of a neural network. It's apparently a steep, a curvy, and not smooth, right? So it remains very challenging to control this neural network well when you combine neural network in these systems. Okay, so what is the idea? So the idea is really we want to combine two things. We want to combine deep learning and machine learning together with control theory. Let me show you a typical pipeline control. So what is a typical pipeline control? In classical control, at least. So first you do system identification. Like you have a bunch of data, and and from the data we have some models, for example, linear models. And then we have a dynamic system, and from this dynamic system we do control synthesis, and eventually we apply to robots. So what is a benefit? Benefit is because we have the bridge dynamic system, and we have a formal control synthesis, we have some formal guarantees like stability and robustness safety. So what is the cons? The cons is first, the systematic part is usually pretty expensive in algorithm and are hard to generalize. For example, it is the wind tunnel test when you want to system ID the aircraft. The first is super expensive, as you can imagine. And second, it's hard to generalize in the sense that if you switch the aircraft, if you switch the wind condition, it's really unclear whether we can still trust the model. And the third cons is the control synthesis in this box is usually a little complex or intractable or conservative. For example, even if I give you a very complicated wind tunnel model, it's unclear how to design a good policy, a good controller from this model, because this model might be too complicated. So sorry, go ahead.
Sorry, one question here is, does this also hold for adaptive control?
Oh no, kind of. So the yes and no. So the good things of adaptive control is adaptive control can adapt a little bit, but the bad things is in adaptive control theory, you have to have the linear like a uncertainty, a parametric uncertainty. Like usually you have some known structure, the unknown things are parametrical. So actually later on I will show how to combine meta learning with adaptive control to achieve fast but rich adaptation. Yeah. Thanks for the question. It's a very good point. So and then I will show you a typical pipeline in learning. So different from controlled. So here learning actually means reinforcement learning basically. A typical pipeline in learning is first I have a lot of data and I do learning in this box. Here I have a circle because usually this process could be iterative. And then we have some policies from this process. And also remember in RL, usually this box happens in a simulator only. And finally, we'll apply this policy in robots. So what is the benefit? The benefit is essentially every benefit we have from deep learning. For example, it's very flexible, and also it could be generalizable, transferable, because we have such a powerful function proximity neural networks. And what is a cons? A cons is pretty much first, it's hard to get formal interpretability, as I mentioned before. And second, deep learning is data hungry. Like we need billions and millions data points to have a reasonable models. So what is today's talk's idea? It's literally combine these things together. How is our framework here? So first, as you can see here, we do not only have learning, we also have physics as a prior knowledge. And we combine with data and learning together, and we get a mixed and a modularized model. By mixed and modularized, I mean part of the model is learned, part of the model is from physics. And then from this mixed model, we do a controller design and the motion planning. And eventually we apply to the robots. So we have two key features. The first one is because this system is modularized, it's very easy to integrate learning and control theoretical result nicely. And the second, I want to emphasize this learning couldn't be arbitrary. We couldn't arbitrarily learn these things using like arbitrarily complex neural network. We need some control semantic regularization, which I will show later. So basically, control the design process will regularize the learning process in some sense. Okay, so we have several key features we would like to pursue. The first one I mentioned before is generalizability. Like for example, if you fly the drone to a new environment, to a new wind, can we still generalize? Can we still like guarantee something? The second feature we pursue is guarantee. Like we wanna at least guarantee like stability and safety. Like if you perturb the trajectory a little bit, you always stay in a bounded tube. The third one is we are looking for compact and efficient repetitions. Again, our goal is running neural networks in real time on small vehicles. So all these things together eventually achieve some new capabilities in robotics, as I presented in the first slide. Okay, so by the way, there are many other people working on these topics, not only me. For example, we are organizing a seminar called Control Meets Learning seminar series, which is around control theory and machine learning. I highly recommend you attend this weekly meeting because it's really cover a lot of cool stuff recently. And the second one is we even have a new conference called Learning for Dynamics and Control Conference. I think for this year, the third conference is the third FRDC conference, and also we have a lot of courses. For example, Caltech CS 159, Stanford, and UPenn have similar courses as well around control learning. And finally, we have a lot of workshops in Boost Learning, Control, and the Robotics conference about control and learning. Okay, so today I will present. So follow the new pipeline combining learning and control. Today I will present the detailed line of work on neural family. Where the idea is pretty straightforward. Is we have a nominal dynamics F from physics, and we have the unknown part G, and we have the first neural lander. The idea is we learn G using normalized neural networks, and the second one is neural swarm. It's essentially learn G in heterogeneous swarms. Like G here is coming from swarm interactions actually. And the third one is NeuroFly. I'm gonna briefly talk about that. Like Florian mentioned, it's going to be combined meta learning and adapt control to achieve online adaptation. Okay, and the last one I'm gonna briefly mention as well is called self exploration, because in the previous three neural X, we all need either humans or experts to collect data. But what if we don't have such expert? Then the goal is to safe learn G without expert. Okay, I would pause for a second to see whether there is a question. Actually, we have a question in the chat box, do we?
Yes, so Manga has a question. His mic is not working, so I can ask on his behalf. His question is, are you making any distinction between safety and stability?
Yes, I do. I will go back. Yeah, I do. It's different.
Okay, thank you.
So in the stability, we don't have something like unsafe region, but in safety we have either chance constraint or deterministic unsafe set, unsafe set. Right. We will back to that point later.
Perfect. Thank you.
Thanks. Okay. Any other question?
I have a quick question. With regards to like, is this kind of setup similar to like a residual policy learning type setup?
That's a very good question. So I was thinking, I think it's in different level. We will back to that later on. So here is more like in the model level, but 100% you can do this in the policy level. So here I'm doing a physics policy plus learn model, and you can actually do control physics. Sorry, here I'm doing physics or like a control model plus learn model, but 100% you can do physics driven policy plus learn policy. Yeah. Actually, in our group, some people is actually doing this idea, like PID policy plus some residual, like a learn policy to guarantee safety, something like that. Yeah.
Okay, thank you.
Cool. So let's get started. So first it's neural lander, and again here we achieve a smooth, fast landing compared to baseline. And the challenge is mainly when the drone is close to the ground, we have something called ground effect. It's pretty complex. Like because the propeller is rotating very fast, the ground will kind of give some force to the drone. And here is a fluid dynamics model. And let's go. And here's a quadrotor dynamics. It looks pretty complicated, but I want you to ignore these models at all because everything is standard except these two terms. The Fa and tau A, I call that residual force and the residual torque. Everything else is actually the nominal dynamics F. So in summary, we have a nominal dynamics F in the left part, which looks complicated, but actually it's really easy to system ID this part. For example, the mass, the inertia, something like that. And the G is the unknown residual dynamics. For example, it covers modeling mismatch, like you model something imperfectly in system ID, and also the ground effect, as we mentioned before. And this part is much harder to model than F. As I mentioned before, you usually need a wind tunnel test, or you need some very good computational fluid dynamics solver to model this. Okay, so given this model, suppose we have a learn Fa and tau A. I haven't talked about how to learn it, but suppose we have learned the approximation of Fa. We call that Fa hat. So what is a controller design? As asked by Arthur, here we are doing a model-based model level like residual, right? So we have two parts in the policy. One part is a SOTA nonlinear controller based on the nominal dynamics. So we design a nonlinear controller based on the nominal dynamics only. And then we design a residual controller, which is based on the approximation of Fa hat, of the approximation of the residual dynamics. And Fa hat here is a function of the policy is a function of the neural network Fa. So yeah, here we are doing residual in the level of dynamics because we estimate Fa hat first, and then we translate it to the policy level.
Is there a reason why they should be additive and not have a policy that depends on the full model?
Yeah, good question. So the main reason is we leverage the property from the robotics dynamic structure, Euler-Lagrange structure. Mm-hmm. In robotics, it's Euler addition, but if it's possible in some other dynamical system, it's not addition, but in robotics it is. And also we have U here. So we have X and U here. So technically, this addition covers a lot of cases because we have U here. But if you only have X here, it's kind of limited. Yeah.
Got it. Thanks.
And you're ignoring the torque here?
Oh yeah, it's just an example. We can have talk here for sure. We will see that in next paper actually. But for Neurolander, we didn't do talk because the talk is really small. The residual talk is really small compared to the residual force, right?
And you're assuming
Cool.
perfect state information?
Perfect what? Measurement information?
State information?
Right. So everything in this talk is state feedback case. Yeah. But it's very easy to design like common filter or some measurement process on top of state feedback controller. But here we basically doing state feedback. So state feedback can mean we can perfectly measure X. We know the state X. And here the X is already a very low level information like velocity, position. So we don't deal with like a pixel level information, right? Okay, so based on this policy, this hybrid policy, we basically have three challenges. First is sample efficiency. As I mentioned before, deep learning is data hungry. So how do we efficiently learn FA hat and make sure it's runnable on small drone? Like we kind of already solved this because we are learning residual dynamics. Let me show you an interesting number. If we learn the full dynamics on our drone, like F plus G together, we ignore the structure on F. It needs 1 hour flat data. But if we only learn the residual dynamics, we only need 5 minutes data. So in this sense, learning the residual dynamics can really make sampling much more efficient. And the second challenge is, as you can see from this equation, we have a control allocation problem because the U, the control action, appears in the left-hand side and right-hand side. In other words, our neural network explicitly depends on U here. So the question is how you solve it, because U appears both here and here. And the third challenge is from the second one actually, is in this framework, and FA is a neural network, perhaps pretty complicated. And how do we show like stability, robustness in control? And also in learning, in the sense of learning, how do we show generalization? Like what if we generalize a little bit to a new domain? And I will tell you for challenge 2 and 3, we solve this by spectral normalized DN. We will go to this detail in the next slide. So what do I mean by spectral normalized DNs? So the key idea is to solve the control allocation is, okay, we can simply use the last time step U in the right-hand side to get the next step U, as you can see from this equation. Actually, we can show if the Lipschitz constant of the deep neural network FA hat is upper bounded by some constant gamma, and we will have the following guarantees on stability. This equation is a little complicated. Let me digest it for you. The S is a tracking error. It's kind of the status trajectory I showed in the previous figure. And the lambda is a control gain. And the LA here is the Lipschitz constant of the neural network. And epsilon M is approximate error of deep neural network. And the rho here is a smoothness of command. It's something proportional to the change into like control steps. So in other words, we show that as long as the deep neural network is Lipschitz the constant bounded by something gamma, the tracking error exponentially converts to some error ball, and the error ball is proportional to the approximate error of the deep neural networks. So therefore, we train the FA hat model. We use spectral normalization to train the model. And interestingly, in learning theory, spectral normalization of deep neural network also leads to good generalization. It's actually stability in a learning theoretical sense. So that means spectral normalization guarantees stable in a sense of both learning and control, which is interesting to note. Okay, so what is let me show, before presenting the experimental result, let me show you some interesting training result visualization. So again, we only have 5 minutes data, and here we manually fly the drone. So we have a human pilot to fly the drone to collect data. And here's a training data trajectory, 5 minutes. And we in a part 1, we kind of move closer and closer to the ground. In the part 2, we kind of randomly fly in the full space. And here is a compare with existing ground effect model from fluid dynamics. So it's why I said in the very beginning, system ID in control, classical control is usually not accurate compared to the learned model. The blue line is the prediction of our model, and the orange line is a couple of different fluid dynamics model, and the green dots are ground truths. So as you can see, we can offer much better model. So here is a very, very interesting 2D heat map of the learned FA, the learned residual force, without and with the spectral normalization. So as you can see, if we have spectral, the x-axis is the velocity of the drone, and the y-axis is the head to the ground. So in the left part is the result with spectral normalization. So as you can see, we can generalize a little bit in a new domain. So everything red to the dashed line is a training set domain where we collect data. And the left part is a new domain. As you can see, we can generalize a little bit. And also clearly you see ground effect, right? When you're close to the ground in this direction, the magnitude of FA is getting bigger and bigger. And also we can see the air drag from the x-axis, right? If you move faster, and you have air drag. The red part is a prediction result without this spectral normalization. As you can see, it's kind of, if you generalize to the new domain, you very quickly you have very big, very unreasonable prediction. So as you can imagine, if you fly the drone in this area, the behavior will certainly be bad. So, and also spectral normalized deep neural networks can guarantee generalization. So it's experimental result, but actually you can guarantee this ability of interpolation and extrapolation in learning theory. So finally, let's see some fun videos. For the first is trajectory tracking problem very close to the ground. As you can see, we try to track a circle trajectory super close to the ground. So actually the drone is not touching the ground, but it's just super close, which is something very hard to achieve if you use like a conventional method. Okay, the second one is the trajectory tracking performance around the table. It's a pretty challenging task because, as you can see, in the boundary of the table, you will have something like table effect. And compared to the baseline, our method can be much closer to the table and have a very consistent performance in the Z direction. But I also want you to note kind of a limitation, right? In the table effect, we need to recollect data and retrain FA because apparently the dynamics is changed. We have a table, right? It's why we will have the neural fly project where we combine meta learning and adaptive control. Because here, if you change the environment, you need to recollect data and retrain FA. Even though this process is fast, but still kind of annoying because whenever you have a new environment, you need to redo everything. Okay, so takeaways for neural lander. Like, let's back to the pipeline I mentioned before. We have physics, very standard, and we have the residual dynamics, and we combine these two things together. We have a mixed system, and we have this hybrid policy, and we achieve some cool performance. And again, training this only need famous data because we are only doing residual learning. And the second, we need to regularize the deep learning process by spectral normalization specified by the control synthesis process. Like we have a number from the control theory to tell the neural network the Lipschitz constant has to be below gamma. And also we guarantee stability on this modularized system. And let's go back to some of the features. First, we achieve generalizability. We can generalize to the new area. And second, we have like stability guarantees. we exponentially converge to some error bar. And these two things together achieves most safe and fast learning. Okay, before I switch to the neural swarm, I would like to pause for a second to see if we have any questions.
Do you care very much if you know exactly the Lipschitz constant of the network, or if you can determine it? Or
That's a very good question. We in this case we are using full layer neural networks, so we are using a very loose upper bound as a Lipschitz. We are doing the multiplication of 2 norm of each layer.
Yeah.
But it is a loose upper bound, but it's okay for small neural network. But definitely for deep neural network, we will care about the Lipschitz, the constant instead of upper bound. But again, for our full layer neural network, it's definitely okay to have upper bound. Yeah.
I'll send you a link to a paper which you might enjoy at the end.
Yeah. Thanks. Yeah. Okay. Let's move to the second one, neural swarm, and different from the neural lander. Here the G is something in the swarm, so we're gonna have new challenge. But the motivation is pretty clear. The motivation is for you who play with drone, probably you know, like if the drone is below some other drone, you will have something called downwash. For example, here are 2 crazy flies, and they are 50 centimeters away from each other, and the lower guy will suffer 9 gram thrust loss from downwash, which is pretty significant. And this downwash will certainly influence the controller performance and the motion planner performance. As you can see from this video, the baseline controller will have this result. And these 2 drones are supposed to stay in the wetlands. But clearly you see something happens here, right? The below drone, the big drone, is kind of suffer from the downwash. So in summary, the interaction matters. It is the reason why prior works require 60 centimeters safe vertical distance. And the second, the prior works only studied 2 rotor blades. The question is, how can we model interaction in 2 and more drones instead of just 2 rotors? And also, like, how we model heterogeneous teams. So, because as you can see from this video, we have a small one, we have a big one. Certainly that difference. So how do we model this heterogeneity? So mathematically, we have some model like this. Here the figure is an example. We have 16 robots, 14 small and 2 large robots, and we also have a ground effect from the ground, same as neural lander paper. So mathematically, the model is like this. Again, to the left part, we have the nominal dynamics, but difference is for each robot have different nominal dynamics. The big one, the large one, they're different. So here's the nominal dynamics for type I. But again, I want to emphasize the nominal dynamics here is pretty standard, and you can systemize it very easily. And the difference is we still have the residual force, residual torque. The difference is different from neural lander is the residual force, the residual torque. Right now, they're function of the drone's neighbors, not only drone's state, but the drone's neighbor state. And also because the swarm is heterogeneous, we have K different types. Like for a small robot, it has the large as a neighbors, it has a ground as a neighbors. So to summarize, we have several challenges. Like first, it's heterogeneous, right? We have K different types. And second, how do we generalize? So here is an image with 16 robots, but probably we couldn't collect data with so many robots. What if we only have data from 1 to 3 robots? Can we generalize to 16? And also, again, we have really limited computational power. It's such a small drone. So that means we have to think about how to decentralize the whole process. And lastly, how do we consider interaction motion planning? Because different from a neural lander here, we also want to do some motion planning. And how do we consider this learned dynamics in the motion planning framework? Okay, here we go. So the key things is we observe when important features in a heterogeneous swarm. We call that heterogeneous permutation invariance. As you can see from this figure, if we switch the position of zone 1 and zone 2, there's no difference for zone 3. In other words, we define heterogeneous permutation invariant function as this. Here's an example. For this function, we can switch the place of x1. We can swap x1 and x2, or y1 and y2. There will be no difference, but we cannot swap x1 and y2. So it is something like heterogeneous permutation invariant. And from this property, we generalize the deep set architecture to the heterogeneous case. We prove in this paper that for any continuous heterogeneous permutation invariant function can be approximated by this structure. It looks a little complicated. Let me digest it for you. And first, the left-hand side is the interaction force for zone type I, the thing we want to approximate. It's a function of its neighbors, and its neighbors has k taps. And first, in the right-hand side, we have encoder phi g to encode the type G neighbors to a hidden state. And then we're going to have superposition in latent space. We sum over all like neighbors and all taps. And finally, we have decode the row, decode this latent state back to the force for the zone type I. So to summarize, we need 2K neural networks for K types of zones, which is good which is pretty much scalable because number goes linear as a type of zones, and also the computational burden, as you can tell from the equation here, also increase linearly as the number of neighbors. Any question? I would pause for a second because this is pretty important for.
So this looks related to graph neural networks.
Yeah, very good question. Exactly. So we actually compare with graph neural a little bit, but the thing is, if you only have 2 or 3 taps, this deep set is usually better than graph neural network. But however, if you have 100, I don't recommend this method because you need to train 200 neural networks. Yeah. Thanks.
Cool.
So just give you a more concrete examples here. Let's go back to zone example. We have a big zone 3, and the zone 3 has 3 neighbors: small zone 1, small zone 2, and the environment, the ground. So in the phi net, we have 3 phi net: phi small, and phi environment. And we sum in the latent space, and we have an encoder for the encode back for the large robot. So here's the data collection process. It's an interesting video to watch. We basically fly randomly with different combinations. By randomly, I mean randomly generalize create the trajectory and fly in some cube. As here is a small, here small large, small large, small large. We have different combinations. So we train only with 1 to 3 robust data, and we fly randomly sample trajectories, and we use artificial potentials for safety because we don't want too many crashes during the data collection process. Mathematically, the data set for robot I is going to look like this. So first, I have neighboring informations from tab 1 to tab K, and also I have the measurement of the residual force and torque. So we're gonna learn on this pair, X and Y pair. The X is neighbors information, the Y is the measurement of the residual force. And again, we use SN to improve generalization. And we cover 12 scenarios. As you can imagine, large, small, blah, blah, blah. The total number is 12. Okay. Here's a very interesting visualization of the learned neural network. I want to show you what the row and phi neural network finally look like. So again, we train only with 1 to 3 robot data. This figure is a little complicated. Let me digest for you. And it shows the heat map of FA of the residual force in different locations. For example, in this figure F, we have 2 big drones above. And if I put the third small drone in different area in this heat map, I will have different magnitude of FA. For example, if I put the third small drone here in my cursor, I will have roughly minus 10 gram FA. Is that clear? And also the dashed line here means ground. It is why when you're close to the ground, you have ground effect, and it kind of cancel some downwash effect. And we have different variations in combination. And in the first figure, we only have ground effect. We don't have other drones as a neighbor. Second one, we only have a small drone as a neighbor. The last one, we have 1 large drone and 2 small drone as a neighbor. So I wanna highlight 2 features. The first one is relative velocity matters. From C and D, as you can see, if we move the drone instead of hovering it, we have a different heat map. And the second information is we have some reasonable prediction. Remember, the training data set only contains 1 to 3 robots, but here is actually prediction the full robot case. So we do have some prediction ability because the heat map is still pretty reasonable. But I will formally show the ability about generalization later. Okay, let's go to the application. So once we learn the FA and tau A, the residual force and torque, the first application is same as neural lander. We can do a decentralized control with learned interaction. So here is a pipeline of a standard control. I remember someone asked a question how we use the residual torque. We will talk about this right now. So it's pretty standard nonlinear control scheme. And the only fancy thing is we have delay composition here because we found that it's very critical for small vehicles, like for a crazy fly. But anyway, it is a pretty standard conventional control scheme. And on top of this, we add the learned dynamics here. So everything in gray is a standard thing. The everything in black is the thing we add from learning the dynamics. So here is how we add the torque. So we add the force in the position controller, and we add the torque in attitude controller. And again, this is from Dept, the structure including encoder and decoder. So we only need to take a few milliseconds on crazy fly to compute FA and tau A in real time. So which is very compact and desired because crazy fly is really limited. So some cool videos. So because of time, I want to only show the 2 videos here. And here's the baseline performance in a swiping task. And again, the 3 drones are supposed to stay in the wetlands. And here's a baseline performance without learned interaction. Right, as you can see from this video, because of the downwash, the error is pretty large. And here's the performance of a neural swarm. As you can see from this video, this is 3 robots almost stay on the wetlands. Yeah, and we have some quantity numbers in different tasks. And the neural network case is always much better than the baseline. And again, I want to emphasize the baseline is not PID. It's a SOTA nonlinear controller with delay composition. We found that if you don't have delay composition, for example, if you use PID, you cannot even fly. For example, for the task 3, for task here. Okay, generalization, the cool part. Again, we only have data collection from 1 to 3 robots. Can it generalize to like 5, 6? Answer is yes. The first, here's a prediction result from 5 robots swiping task, 2 large and 3 small. So the first figure is a trajectory. As you can see, the neural network case with learned dynamics is very close to the desired trajectory. The second figure is a ground truth FA, ground truth residual force, versus the prediction. As you can see, the prediction is still pretty good. And further, we can generalize to 16, right? So as you can see in this video, we can apply the trained dipset, trained neural networks in a 16 robot. It's a very challenging 3-ring tracking task. We have 3 rings, and they intersect with each other. And again, it's heterogeneous. And we eventually achieve 24 centimeter minimum vertical distance. And recall the prior works require at least 60 centimeters as a safe vertical gap. Okay, I want to quickly go through the second application after we learn this residue dynamics. It's motion planning. This neural net only covers control, and here we also covered a little on motion planning. And we integrate learn dynamics with a 2-stage planner. I want to give you just a high-level idea. What do I mean by 2-stage planner? The stage 1 is a sampling-based planner, like AORT style. And the stage 2 is the optimal control-based planner. We use the sequential convex programming to solve it. In the stage 1 is ORT kind of searching algorithm. Here we fix the trajectory of the small robot in the blue, and we search for the orange robot, the large robot. And I want to emphasize it's different from conventional AORT because we consider interactions here. For example, we reject the 13 tree here for the big robot because it introduced 2 large falls to the blue vehicle. We don't want such trajectories. And the second phase, please ignore these equations. I want to emphasize it is optimal control-based motion planning, and it's non-convex, so we use sequential convex programming. And the most important thing is we can directly control the interaction magnitude here.
Sorry, just a question here. Are
Sure.
you assuming that the trajectory of the blue robot, of the small robot, is actually fixed and given, or is it changing over time as you are building the tree that is the best response to that?
Oh, good, very good question, because we want everything decentralized. So when we plan for the large one, for the orange one, the blue one's fixed. We're doing that alternatively. And when we plan for the blue, the orange is fixed. When we plan for the orange, the blue is fixed.
I see.
Yeah, we don't plan the joint space because it's too expensive.
Okay.
So the stage 2, maybe you're not that familiar with, but it's fine. The most important thing is first is optimal control base. Second, we can directly control the magnitude of the interaction. So here's some result I want to present. And here's a searching result from AORT stage 1. It is a reason why we want a stage 2. As you can see, it's not smooth, right? And the second one is planning with interaction falls in a stage 2. Like as you can see, the trajectory is very reasonable. The tracking is very close to the planned trajectory, and the large robot is at the bottom because it's more optimal in terms of interaction falls. And as you can see here, the interaction falls in the green didn't go beyond the constraint. We have some constraint on the interaction falls. And however, here is the planning without learned interaction in the stage 2. And first, you can see the large robot is at the top, and also it has constraint violations. The interaction falls of on these 2 small gaps beyond the constraints because the large one is on the top. It created too much downwash for these 2 small robots. Right. Awesome. So let me summarize. Neural swarm takeaway. Let's go back to the scheme. We have physics, and then we have the learned dynamics from DeepSet, and we have a modularized swarm, and we apply it to decentralized control and two-stage planning. And the importance is we need some knowledge like permutation invariance symmetry from the structure of the swarm. And the second, we can prove stability and safety. And here, safety is different from stability in the sense of motion planning. We can guarantee like interaction falls, we can guarantee the constraint. And go back to the features. And first, we do enjoy generalizability. We can generalize from 3 robots to 16 robots. And second, we do have a compact and efficient representations because we can run it in real time on small vehicle. And these things together achieve safe close proximity flight. Okay, awesome. It's a bit over time, but can I like, do you want me to spend like a few minutes to go through this meta learning plus like a adaptive control idea? Like probably two minutes is enough.
I'm very much okay with that.
Okay, thanks. Yeah, sorry again. I'm late in the beginning. It's new because Caltech network is really horrible in the morning. Okay, the NeuroFly and different from NeuroLand and NeuroSwarm, as mentioned by Florine. What if the environment is changing? Can we combine adaptive control together with something? So like the key things is we found the unknown part of real dynamics is usually governed by the environment C. So for example, the C here could be the wind, like the drone flying in different wind, we have different C. And here is we have a histogram of G, the residual dynamics in different C. As you can see clearly, it is shift when we move to a new C. And the key idea is we want to approximate G as a combination of some feature phi, which is function of X only, and times a latent state AC, which is a function of C only. And this phi is some representation to be meta-learned from meta-learning. And this A is some latent state to be online adapted using conventional adaptive control theory. That is a key idea of this NeuroFly work. And I want to skip how we use MAMO, but we essentially use MAMO model agnostic meta learning to train its phi. I want to skip it how we learn it, but this part is pretty a variant of MAMO. You can go to the paper if you are interested. The key idea is we have data collected from different Cs, and once we learn this representation phi, we design the adaptive control controller as a function of this representation phi. So that means we adapt to A, the latent state, as a function of previous A, previous trajectory and a phi. And we can also guarantee stability and robustness under some assumptions. And here is a video. I want to quickly show it. And without, as you can see, without learning this phi, it's very hard for a drone to adapt when you can have a time variant wind. But if we have this adaptation, as you can see, even if we have time variant wind, the drone can very quickly stabilize. Okay, awesome. So a takeaway, and because it's ongoing work, you can find a preliminary on archive. It's a tentative takeaway. Is again, we have physics, plus meta learning, and the key is the policy part. The meta learning provide efficient representations for the adaptive control policy, and again we can guarantee stability, and we have generalizability from meta learning, right? We can generalize to different wind, different environment, and we do learn the compact and efficient representations phi from meta learning, and this achieved flying in changing environment. Okay, awesome. I will skip the sorry.
I can ask a question.
Sure, go ahead.
So in adaptive control, you typically have the property that you learn, the parameters of the system on a need-to-know basis. So
yeah,
you guarantee that you're going to learn the true parameters, but good enough parameters to do the task at hand. Do you have the same property here, or?
Yeah, exactly. That's a very good question. That's called persistent excitation. That means, so the goal of so once we learn this phi, the goal of adapt control is not to recover A. It's just to adapt A such that we can finish the task. We don't actually care about whether the A convert to the ground truth A. We only care about whether we can adapt A to finish the task. So, but however, in conventional adaptive control, the phi is usually designed. It's easier, but here it's meta-learn as a key difference. We meta-learn the representations for adaptive control.
Got it. And the proofs of stability and robustness make some use of Lyapunov.
Yeah, for sure, exactly. You need a jointly Lyapunov function on A and the tracking error, basically.
Got it. Cool. Thanks.
Awesome. Sorry, I will skip the civilization part. But the idea is if you don't have expert to learn this G, the goal is to you need to quantify uncertainty. You need to quantify domain shift. Because if you collect data in source, you want to generate a target. You want to quantify how much domain shift you have. You want to quantify uncertainty. And you want to design motion planning on top of this uncertainty to trade off exploration and exploitation. Okay, if you're interested in this topic, check out the paper. Okay, just very quickly summarize. It's actually copy the previous slides. How we combine learning and control to have a new scheme, new pipeline. And the features, the key features is first, we have residue here. And the second, the control, we need a control semantic regularizations for learning. And because the system is modularized, we can combine learning and control theoretical result together. And we want some key features, including a generalizability guarantees and compact efficient repetitions. And these things together finally achieve new capabilities in robotics. Okay, thank you so much. Here's all my collaborators. If you have questions, I'm very happy to answer them. And here is a reference. So I think I will upload the slides later on. Okay, thanks. Any questions, or do we directly move to the next session?
I have a few questions, but I'm waiting in case other people have any questions.
Yeah, I have a question. So for any safety guarantees, so for example, collision avoidance among the robots, is that purely done through the motion planning part? Or is there also maybe like some future ideas to combine this with like some safety filter, like a control barrier function to avoid collisions, for example?
Very good question. So in our framework, we do have a safety in motion planning, but we don't have the safety module in control. Okay. Here, as you can see, I'm trying to find the cursor. Okay, here, as you can see, the equation here is a safety guarantee. We guarantee that the distance between two robots is lower bounded by the collision avoidance, like parameters R. But however, this only happens in motion planning. So okay. So in the control, you're definitely right. If you want to guarantee safety, you probably need a control barrier function, or like some other things to filter the learn policy. But however, I want to mention that the learn FA and TOE will be still useful in control barrier function, because that will influence the control barrier function as well.
Okay, yeah, I see. Thanks you
for the question. Sure. Okay, do we
any other question?
Another question?
I have a super quick question. So like most of the work you have is focused on quadrotors, and like we're wondering, do you see generalizations to other platforms potentially?
Oh, very good question. We tried in our lab. So I have my friend actually tried it on some rocket models, which is interesting. But and you can also do it in a walking robot. And technically, this framework is pretty general, especially in Neurolander scheme, because again, this in a Neurolander scheme, the residual term is a function of X and U, which is pretty general. You can capture almost all like a multi-name mismatch, right?
Yeah. Okay. And thanks for the talk.
Thanks.
And your baseline controller, your reference trajectory tracking controller for the Neurolander paper, is that based on sliding mode control?
Exactly, that's based on sliding mode control with well-tuned gain.
Okay, all right. Yeah, I was just wondering. Thank you.
Okay.
So I had a question about the final work on safe exploration.
Sorry, I didn't cover that part, but
oh no worries. I think I got the broad idea, but I was wondering, how do you actually quantify the uncertainty when you move to
Oh,
a new.
You really ask a the most important question is why. So we didn't use Gaussian process because we found this data is so non-IID. Like, cause if you have data in a slow landing, so we eventually want something like fast landing. As you can see from this video, landing very fast, like corresponding to this orange trajectory. We want a safe and a fast landing. And this green one is fast but unsafe landing, just crash onto the ground. The blue one is the slow and safe landing. So if you have a slow landing data, pretty much you only cover the data here, and you wanna quantify uncertainty in this target domain, which is different. It's actually the covariance shift problem. That means the mapping from X, Y is fixed, but however, the target and the source, they have different distribution on covariant X. So we propose a framework actually from the postdoc Angie's previous work called robust regression, which is a framework to quantify uncertainty under covariance shift. Yep. So the key idea is you need to quantify covariance shift first, and then have a robust way to give prediction in the target domain.
Mm-hmm.
Right.
But I'm assuming you make some assumptions about the parametric model of P target X and P source.
Right. Excellent question. So yeah, so you can do two ways in the paper. We have two ways. One is linear features. Another is you can deep learn the features. Like the idea in the meta learning part, NeuroFly, you can train the representation first, and then quantify the uncertainty on the features. But you need a fixed parametrical form to quantify the uncertainty.
Gotcha. I have one final fun question, which is all your robotics experiments are really awesome. I'm wondering how much can you tell students how long did it take for you to get those experiments, and how many robots did you crash in the meantime?
Oh, that's a lot. That's why in the motivation part, I really wanna because folks, I really feel it's different in this box and in this box, because we really care about the crash. I crashed like probably hundreds of times. The good thing is for Crazy Fly, you don't care about the crash a lot because it's so light. It's pretty robust. However, for the big drones, the Neurolander drone, if you crash, you need to spend like hour to fix it. So we need to be very careful to design the policy to be able to handle this. But so I recommend Crazy Fly if you want to do some crazy tests on drones. I recommend some small vehicle instead of big vehicle.
Yeah.
Awesome.
Great. Thanks very much for the talk. This was very, very exciting, very interesting, very fresh. Thank you.